Alright, here we are. We're going to be talking about air currents. And to do air currents, we need to talk about convection, okay? Basically, say we have the surface of the ground right here. Not a very good ground. Let me try that again. Alright, there's the ground. We said that sunlight hits here. Sunlight does not particularly warm up the air as it goes through it. Otherwise, it'd get hotter at the top and cooler at the bottom. But actually, when it hits here, then it's re-released as infrared or heat, basically, and it heats up the atmosphere at the bottom, both by radiating back from the Earth up into the atmosphere, but also because the air touches the Earth, some of it's by conduction. Both between conduction and the infrared that's being radiated back off the surface, it starts warming up the air, and it warms up the most down here at the bottom. So if you have these air molecules, okay, as they heat up, they're going to get farther and farther apart and move faster and faster, which makes them less dense. And since they're less dense in the air around them, they will start to rise. Now, as they rise, they're going to start cooling down and getting closer together again, which means they're getting more dense, and they're going to sink back down, all right, to the bottom. And then as new air is rising, it's going to suck this air in to take its place. And so you get this convection current, okay? A convection current is just this rotating current of air as it heats up and gets less dense, and it rises, and then as it cools down and gets more dense, it sinks, and you have this circuit going around on a circle base. Now the same thing's going to happen at the Earth, and where is the Earth going to be getting the most heat is usually at the equator. Now granted, based on the tilt of the Earth and what time it is, at the equinox, which is the time when it's not tilted toward the sun or away from the sun, okay, it's tilted, but the sun is to the side of it, so to speak, of the tilt, as far as the tilt goes. So it's hitting right at the equator, okay? That's where you have equal day and night of equal length, 12 hours, okay? Happens in the fall and in the spring. So you have spring and fall equinoxes, all right? And you have equal day length at that time. All right. Now, as it does that, the sun's hitting most directly and the most concentrated, if you will, at the Earth's surface. So right here at the Earth's surface, at the equator, is where the air heats up and rises. Now, as it heats up and rises, eventually, obviously, at the North Pole, it's going to get cold and it would sink. And so you could have this big convection current of air going. But actually, it's a little more complicated than that. And one of the things that complicates it is that the Earth is spinning. Okay, it's spinning to the east. Okay, every day it makes a complete revolution, or rotation, excuse me, not revolution, that's the year. But it takes a rotation around its axis, and so this movement makes it look differently. For example, if I'm on a merry-go-round, this is me and there's someone else across, and I throw a ball at them, if I throw it straight across where I am now, by the time it gets there, they will be over here. And to them, it will appear like I threw the ball toward them and then it curved off over to this other side. But in reality, they moved. Well, the same thing happens to the Earth. Okay, this air is trying to come straight down, but as the Earth is moving underneath it, it appears to us as though it curves like this. Okay, and on the other side of the equator, coming up, instead of coming, it looks like it's coming straight up, but as we move, so it looks like it's curving this direction, okay? And so one, this keeps it from being just straight north and south winds. It makes them twist and curve from the east in this case, and we'll look at other examples here in a minute, but it changes the direction they're coming from, and also it disrupts this big convection current. And instead of getting one big one, we have several smaller ones. This deflection, or change in direction of these winds, this is known as the Coriolis effect. Okay, the Coriolis effect is basically just when winds appear to move straight up and down, or they do move straight up and down the surface as the surface rotates beneath them. To people on the surface, that's us, it appears as if they are curving and coming from a different direction. Okay, and that's this Coriolis effect that causes that. Now, because the rotation of the Earth and these other factors is a little more complicated than what we said, so you still have air rising at the equator, Okay, it's rising, and from the side it's rising. Okay, but let's just say make this, whoops, it's probably a little high, but that's about 30 degrees. And then up here you have about 60 degrees. Actually, that's not too far. And then up here at the equator you have 90. Okay, as this air rises, it splits, and on the northern hemisphere it's going to come up this direction. On the southern hemisphere it's going to go back this direction toward the 30 down here. Okay, as it rises up here, it's going to cool off, and it's going to begin to sink. Okay, at 30 degrees. Alright, now this air down here would rush down, take its place, and you just have this little convection circle going on there. Now we know at the North Pole it's going to be coming down because it's getting colder, but as it goes down here, it warms up, and as it gets to 60, it begins to go up. Okay, and then it curls back to the North Pole where it gets colder and eventually going to go back down. Okay. Now that means that some of this air here is going up at 60 is going to come up and go back down here. Alright, and it will be pulled down when it hits this air here. So it kind of gets caught like a gear between those two things, and it turns it that direction. So we have actually 3 cells or belts. Keep in mind these are 3-dimensional going all the way across the globe here. Alright. Alright, and keep in mind they do not go straight. Okay, these are coming down, so if they're coming down, they're going to curve this way. If they're going up, like this one, they're going to curve up like this. Okay, and so as they're trying to go up and it's turning, they're going to curve like so. Alright, and then these up here are coming down, so they are going to curve again like so. Alright, now these same things would happen but in opposite directions. You would have a circuit back here, it's trying to come up, it would come like that. Okay, these between 30 and 60 would curve Alright, they're going to curve like this, okay? And then finally you would have the polar easterlies, which are going to be kind of like these other ones up here, going up that direction, like so. Okay? And so we would have the same weather patterns, just kind of flipped over on the other side, and you'd also have these cells going around here. Now, notice at the equator, since the air is rising, therefore it's leaving, and therefore that's leaving kind of a partial vacuum, if you will, here. So this is an area of low pressure. Okay, and they're coming together and coming down. The air's coming down and pressing down on the Earth, if you want to think about it that way. So this is an area of high pressure. Okay, back up here, once again, they're both coming up, so you would expect this to be a low pressure zone, an area of low pressure. And finally, at the pole where they're coming down, again, you would expect that to be high pressure. Okay, so you have these alternating high, low belts. And the same thing would go on down here to get high, low, high, low. Now, at these low areas where the air is rising, since the air is going out and up, you don't get much horizontal action. And so sailors who would reach near the equator would hit, there's no winds, and they would hit no winds, and they just kind of drift along, and they called this the doldrums. Okay, because there weren't much happening. If you're in the doldrums now, we say someone's in the doldrums, that means they're just, I don't feel like doing much, just kind of sit around. If you're in a sailing ship and there's no wind, that's all you can do. You just kind of sit there and wait for the current, hopefully to carry you to somewhere where there is some more wind. Alright, now, once you get off the equator, these winds on either side are the trade winds. And the trade winds are very good winds, and they would carry them, especially people over Europe coming over to the New World and things like that. These were very good winds, and therefore they are called the trade winds, because all the ships that were trading with various things from one country to another used those to get there. And so you have very good trade winds. These are called the northeast trade winds because they're coming from the northeast to the southwest, and winds are named for where they come out of. Okay, these would be called the southeast trade winds because they're coming from the southeast going up to the northwest. Okay, now at 30 you have this high pressure belt. Once again, you have vertical action, this time going down. You don't have much horizontal action, so there's no winds. These were called the horse latitudes. Often as people were getting here, they were bringing soldiers and and horses and stuff for their soldiers and armies that are trying to conquer these new worlds. And horses drink a lot of water and eat a lot of food every day. They don't digest particularly well, so they have to eat a lot of stuff. And they're saying, hey, we're kind of drifting here with no winds, and it's far into the trip. We're not getting where we need to go very fast. So we will either, one, eat the horses for food because we're getting short on food, or we would get rid of the horses, toss them overboard so that they don't eat up all the food and water that we need to survive. And so sometimes there would be horses out floating in the water because they've been ditched by these ships. So they were called the horse latitudes. Okay. Then above that you have some more good winds. These are called the westerlies. All right, westerlies. And finally up here you have the polar easterlies. All right, easterlies. And then, of course, you have high pressure up there, low pressure here. Now, the high pressure, generally when we think of high pressure is associated with fair, sunny weather usually. Okay, if we have a high pressure system move in, it means there won't be any rain. Low pressure indicates that there might be. And so this 30 degrees latitude area, along this, there are many, many deserts. The Sahara Desert in the United States. You have, I mean, not Sahara Desert, sorry, Sahara Desert in Africa. We have the Mojave Desert out in the west, the Arabian Desert in the Middle East. Australia has one called the Great Victoria Desert. But all these deserts, a lot of them are located either on 30 degrees north or 30 degrees south because these are high pressure areas and therefore there's not a whole lot of rain. Keep in mind, polar areas, yes, you say, oh, there's all this snow and ice, but there's not much moisture falling, and those are also kind of in a sense deserts. So high pressure areas tend to indicate less rain and things like that, and so they tend to be more deserty type areas. Alright, so we'll leave you, this is their version of the same drawing on the other paper. This one's probably a little easier to see, but just wanted to kind of show you how that stuff formed. But basically you have low areas at the equator and at 60. You have high pressure areas at 30 and the North Pole, very many deserts. At these areas where you have high and low pressure areas, you don't have very good horizontal winds because air movement's either up or down vertically. And so you have the doldrums along the equator where the sailing ships were not moving more, horse latitudes where they didn't move and so sometimes threw off horses or ate the horses because they were using up too much of their supplies. You have trade winds, though, that have very good currents, and there were a lot of this was the middle around the equator where people were going back and forth from the old world to the new world. And then you have westerlies, which are also good, and then you have a low up here and the polar easterlies at each end. All right, and that just kind of gives you an idea. You need to know where these are located, what they're called, what direction they go, and be able to label that if you can. All right, and that's it for Chapter 30. Let's move on to Chapter 31. There's a whole lot more in Chapter 30 about oceans and stuff like that, but we're not going to spend a lot of time on the ocean since we are not near one.